Okay, last bit. Questions 14 through 19. A constant force of 30 newtons is applied tangentially to the outer edge of a merry-go-round. The following diagram shows the view from above. The merry-go-round has a moment of inertia of 450 kilogram meters squared about a vertical axis. The merry-go-round has a diameter of 4 meters, which means that its moment arm is 2.00 meters. The merry-go-round starts from rest, and the force is applied for 1 complete revolution. Show that the angular acceleration of the merry-go-round is 0.1 rads per second. Oops, rads per second squared. Typo. Okay, so we're going to use torque equals F cross R. The cross product, as you know, is the angle between the moment arm and the force applied. So this is at 90 degrees. Sine of 90 is 1. The force applied is 30 newtons times the distance of the moment arm is 2 meters. So the torque acting is 60 Newton meters. And that equals, the other equation for torque is I times alpha. So that equals I, the moment of inertia, 450 times alpha. So I'll solve for alpha. Alpha equals 60 Newton meters over 450 kilogram meters squared. 60 divided by 450 is 0.133 rad per second squared, which is approximately equal to 0.1 rads per second squared. So IB expects you to show your unrounded answer. The IBO wants to see that unrounded answer so they know you didn't cheat. Number 15, calculate for the merry-go-round after 1 revolution the angular speed. We'll assume that this object starts from rest, so the initial angular velocity is 0 rad per second. The final angular velocity is unknown. Angular acceleration is 0.133 rads per second squared. And theta is given 1 revolution. 1 rev is 2 pi rad. So I'm going to use the expression or the equation omega final squared equals omega initial squared plus 2 alpha theta. Omega final squared equals 0 plus 2 times 0.133 times 2 pi. That gives me omega final squared times 2 times 2 times pi, which is 1.675 rad squared per second squared. Take the square root, and by that I mean raise it to the 1/2 power. Omega final equals 1.29 rads per second. Calculate for the merry-go-round after 1 revolution the angular momentum. So the angular momentum is I times omega. This omega is now the omega final that I calculated before. The moment of inertia is provided, 450 kilogram meters squared, times this angular velocity that we had just calculated, 1.29. 450 times 1.29 gives me a value of 582 kilogram times kilogram times meter squared times rads per second. Oh yeah, a lot of units in angular momentum. Kilogram, meter squared times rad per second. Okay, a child of mass 30 kilograms is now placed onto the edge of the merry-go-round. Just imagine what this little kid is going to do. This little kid is going to change the moment of inertia for this system. No external torque acts on the system. Calculate the new angular speed of the rotating system. So now we're going to treat the system like it's in rotation. It's rotated still one time. We've put a kid on here, and now we have changed the moment of inertia. So this is a conservation of angular momentum problem. Delta L equals 0. That means that the moment of inertia before this kid was added equals the angular momentum before the kid was put on the merry-go-round equals the angular momentum after he was put on or she was put on. Okay, so the angular momentum before we've already calculated, it's 582 kilogram meter squared rad per second, and that's equal to the new moment of inertia times omega final. So I need to calculate this moment of inertia. I don't know why I put in parentheses. I think it's because I meant to say that this is the total moment of inertia equal to the moment of inertia of the kid plus the moment of inertia of the merry-go-round, which is 450. So how do I get the moment of inertia of the kid? You use your data booklet. Moment of inertia is mr squared. The kid has a mass of 30 kilograms. At the edge of the merry-go-round, he rests or she rests 2 meters from the axis of rotation. That's a moment arm of 2 squared plus 450. 30 times 4 is 120, so this becomes the final moment of inertia is 120 plus 450, 570 kilogram meter squared. So this is here. This is 570 up in here. So the final angular velocity is 582 divided by 570. 582 over 570, and I get 1.02 rads per second. Okay, the child now moves toward the center of the merry-go-round. Explain why the angular speed will increase. Just imagine his moment of inertia, or his mass, is no longer on the edge. This kid is sitting right here now, so they are at a distance of 0 meters from the axis of rotation. So the complete explanation is that by moving to the center, notice the British spelling versus the American spelling, by moving to the center of the merry-go-round, the moment of inertia of the system decreases. Since angular momentum is conserved, the angular speed must increase. Best explanation. Calculate the work done by the child in moving from the edge to the center. Please note, this is the work equals the change in kinetic energy theorem. Work equals delta E sub k. We know that we know what the initial angular velocity is. We calculated it here. So initially the kid is at the edge. We got what the angular speed was when the kid was on the edge. We now need to get the angular speed of the kid when he's at the center of the system, and then we'll use that to calculate our delta E sub k, and that's the work done. So to figure out what the speed is, we have to again apply the angular momentum conservation. Initial angular momentum equals final. So initially, with this kid sitting on the edge, we have 570 times 1.02, that's the initial condition now, equals the final condition. We go back to just having a moment of inertia of 450, only the moment of inertia of the merry-go-round itself, times our new omega final. So omega final is 570 times 102 divided by 450. Omega final equals, we calculate 570 times 1.02 divided by 450 equals 1.29 rad per second. Okay, and then we know that work equals delta E sub k, which is 1/2 I final omega final squared minus 1/2 I initial omega initial squared. So I'll plug in 1/2. I have the initial moment of inertia for the kid and the merry-go-round is 570. times 1.02 squared minus 1/2 times 450 times 1.29. Notice that this is the same as we calculated up here. So this change in kinetic energy is the work. Work equals, give me one moment while I calculate for you. So nice. Didn't mean to hit that. Apologies. 0.5 times 570 times 1.02 squared minus 0.5 times 450 times 1.29. 1/2 I final omega squared. And I get a value of minus (1/2 times 450, whoops, times this squared. Oops. My bad. I had these reversed. This should be, the final is 1/2 times 450 times 1.29 squared minus 1/2 times 570 times 1.02 squared. That's what you get when you rush. So I have the work equals 77.9, so I'll round up 78 joules. 78 joules of work were done by the child in moving. So I apologize if you were to ever make this mistake and you have like negative work, even though it should be positive work. Just reverse your signs, or just note that I made a mistake. The initial angular momentum was what we did before, so I had it up here and I reversed it down here, but fortunately I caught it. You'll sometimes make mistakes. Everyone does, just as long as you catch it. So I hope you found this video helpful despite this bit at the end. Continue to study, and thanks for watching.